Hello everyone, my name is PinjunZheng. I come from Harbin Institute of Technology in China. The topic of my presentation is a measurement fault elimination method in one-dimensional Fourier phase retrieval. And this is the outline of my presentation. Firstly, I'll give a brief introduction of our work. Secondly, I'll give an illustration of the theory of phase retrieval. The theory is not proposed by us, but is the basis of our work. Then, I'll introduce our proposed measurement search method and then show how to modify the reconstruction algorithm to eliminate the measurement fault. Finally, I'll give some experimental results and conclusions. Phase retrieval is a problem focusing on how to recover a signal from the magnitude of a linear transform measurement, which is called diffraction pattern or magnitude spectrum. It was originally proposed in the field of crystallography, and it also widely appears in many other fields today, such as processing of radar signals and astronomical imaging. The physical process of phase retrieval is to make a linear measurement of a signal and then take its magnitude and then square it. Because this process will lose phase information, it is called the phase retrieval problem. The relevant variables of phase retrieval problem are shown on the slide. Because of the modular operation, the entire process is a nonlinear process. Actually, our goal is to recover the original signal from the magnitude squared spectrum, which is equivalent to recovering the lost phase. Note that the measurement matrix here is usually known beforehand. The most common one is the DFT matrix. In theory, it assumes that the Fourier magnitude measurement can be accurately obtained. However, in practice, there may be some faulty pixels in the detector that pass incorrect values. For example, in some measurement process, it may include pixels that provide zero intensity values, that is, dead pixels. In X-ray or electron diffraction experiments, the signal in the central part of the diffraction pattern is often missing because of a direct beam or due to a hole in the detector. For the cases where there are some wrong values or missing information in the measurement, the quality of the phase retrieval reconstruction results will be reduced, sometimes even wrong. A simple experiment is shown on the slide. At a small range of solenoids in the central area of the magnitude squared spectrum will cause considerable errors in the recovery results. The phase recovery algorithm used here is Gershberg-Sexton algorithm. In this paper, we proposed a measurement fault elimination method applied to one-dimensional Fourier phase retrieval. Our solution can be divided into two steps. Firstly, we get location information of 40 pixels by comparing Fourier magnitude of different oversampling multiples. Then, using the location information acquired before, we modify the recovery algorithm to obtain an accurate reconstruction. This is the theory of phase retrieval. Firstly, the mathematical expression of the phase retrieval process, as we said before, is linear transformed, modular, and then squared, usually accompanied by noise. As we consider Fourier phase retrieval, the measurement matrix phi h is equal to matrix that consists of the first n columns of the m times m DFT matrix. Here m is greater than n. As for solution of phase retrieval problem, we generally treat it as a non-convex optimization problem. For this kind of non-convex optimization problem, there is no non-general closed-formed solution. There are some kind of iterative algorithms, one of the most popular ones being alternating projection algorithms, which was pioneered by the work of Gilbert and Sexton in 1970s. An alternative to solve the phase retrieval problem is based on nonlinear optimization. This kind of method usually relies on the observation that describes a set of quadratic equations which can be rewritten as linear equations in a higher dimension, such as semi-definite programming-based algorithm. In recent decades, plenty of new algorithms were proposed, such as Jasper, Dolphin, Vertical Flow, Prime, TSPR, and so on. The phase retrieval measurement process is sometimes contaminated by local cell noise, which causes measurement fault. This paper considers the typical situation where noise appears in the central area. The picture on the slide shows a schematic diagram of local measurement fault. It should be noted that under normal circumstances, we cannot know where the boundary between the local measurement and the faulty measurement is. Next, I'll introduce a method we propose to eliminate measurement fault. Considering the formula of the DFT matrix, we can derive a relationship of DFT transform under different oversampling multiples as shown on the slide. Fourier transform results will have the same value at different positions under different oversampling multiples, but 40 pixels won't. That's what we can utilize to search out these 40 pixels. In other words, obtain the location information of 40 pixels. This is a demonstration of a 16-point DFT 40 pixels search process, in which we assume there is a 40 pixel at position 4. We can see that doing two comparisons between three measurements of 1 time, 2 times, 3 times oversampling is enough to determine the 40 pixel. A detailed description of the search process is shown as an algorithm on the slide. We explained the important variable used in it. Since we get the location information of 40 pixels through the search algorithm, then I'll show how to use it to modify the recovery algorithm. We take the greedy-based algorithm as an example. In order to remove the modular operation, we rewrite the measurement formula. Combined with sparsity prior information, greedy algorithms such as Jasper can solve the optimization problem on the slide. As we have obtained the set M through the previous steps, here we assume the size of M is R, which means there are 40 pixels in the measurement data. Therefore, our next step is to abandon this 40 data and then construct a new optimization problem with the remaining correct data. This is pretty easy to realize. We just need to simply multiply the measurement matrix by a simple matrix by left. A simple example is given to show this process. Then, using this new measurement matrix, we can construct a new optimization problem without using faulty data. At last, we carried out two simulation experiments. The first experiment is explore the oversampling multiple cost of the 40 pixels search algorithm. The results show that the longer the signal length, the lower the oversampling multiple required to complete the 40 pixel elimination. And for less than 1040 pixels, the average oversampling multiple required to search for all 40 pixels is no more than 5 times. which is acceptable in practice. The second experiment is a reconstruction experiment of phasor retrieval. Here we use Gaspar algorithm to test our method. The results show that if the faulty pixels are not eliminated, the reconstruction result of the Gaspar algorithm has a certain error, but after adding the method of pre-removing the faulty pixels proposed in this paper, this error is effectively eliminated. Finally, I would like to make a conclusion with this presentation. In the paper, a method for eliminating measurement fault in Fourier phasor retrieval is proposed. Our method can be described as two steps: searching measurement fault and modifying the reconstruction algorithm. Numerical experiments show that the method proposed can effectively eliminate the inference of faulty measurement, and the oversampling multiples cost of this method is relatively low and can be used in practice. Okay, this is the end of my presentation. Thank you very much for your kind attention.